So I have now described a method that you can use to collect cell test data in order to fit an enhanced self-correcting equivalent circuit cell model to describe how that cell works. There's probably enough information in what I told you for you to be able to write your own MATLAB code in order to implement that. But I have saved you a little bit of trouble by creating a MATLAB toolbox of functions and data that you can use to exercise that toolbox. So the toolbox is able to process the open circuit voltage data and to process the dynamic data to come up with a full enhanced self-correcting cell model for different cells. In this section, I introduce the toolbox first, and then in the next topic, we'll look at some results from the modeling to give you a feel for what might be achievable for different types of cells. This is an introduction only to the toolbox. I guess my desire here would be for you to go through this section and say, oh, okay, I see the main components of the toolbox, and then to try the toolbox functions on the data that is available on the book website to see how it works, but also to open up these MATLAB M files and look at them line by line to understand how the MATLAB code implements what we have already talked about here. So what we've talked about here is helpful. Having an overview of how the toolbox works is helpful, but I think the greatest learning is achievable only if you put them side by side and look at them and maybe even put some breakpoints in the code to see what happens at intermediate places and plot some intermediate steps and so forth. I don't promise that this toolbox is the best way of doing things. It's simply one way of doing things, and maybe you'll find even better ways. And if you do, please let me know. That would be fantastic. We have functions in this toolbox, functions that are used to create the model from data, and then another function that's used in order to use this model to simulate what would happen in some other usage scenario. And we've already talked about the open circuit voltage testing that must be done and the dynamic testing that must be done, and both of these result in test data. So the blue boxes represent a lab test, and the yellow boxes represent some kind of data, and the green boxes represent a MATLAB procedure or function that is doing something. So the open circuit voltage testing produces test data, and we saw that a couple sections ago, what that would look like. And we saw how we would process that data to give us the efficiency of the cell, coulombic efficiency at those low rates, and the capacity of the cell at those low rates, and the discharge and charge curves, and the open circuit voltage relationship, and so forth. The process OCV.M is designed to do all of that. It reads in the test data and it writes a MATLAB file, a MAT file, that contains the OCV relationship inside of it. The dynamic testing produces more test data, and the process dynamic.m reads the test data from the dynamic testing. It also reads in this open circuit voltage relationship, and it does this process that we just talked about of guessing what gamma is, and based on the value of gamma, it finds the best parameters it can for everything else, and then optimizes the hysteresis gamma until it comes up with the best model that it can find. And that gets saved in a data file, a MAT file, which is the enhanced self-correcting cell model for that particular data set. So again, blue equals lab processes, yellow equals data files, green equals processing by MATLAB functions. So all the code is written, but please open it up, have a look, and see what's going on. then to use the model, this is what we do. We would like to simulate this cell model to predict how the cell would respond to different profiles of current versus time. So I provide to the simulator cell current as a function of time. I provide the initial state. What I mean is, what is Z at time 0? What is hysteresis at time 0? What are the IRJs at time 0, the currents through the resistors at time 0? Given all that, we also load in the enhanced self-correcting cell model parameters. That goes into something called simcell.m, which is the simulator, and it produces some predicted cell voltages, and actually the internal states. It produces all of these as a function of time as well, if you'd like to examine how does SOC change, how does hysteresis change. This figure is an example of the output of simcell.m for the data set that was used and shown in the earlier section that was collected for a particular cell in the lab. And the blue line, if you are able to distinguish those there, the blue line is the truth. That was what was the function of voltage versus time measured in the lab, and the green line is what the model says. So I realize that these are a little difficult to distinguish in this plot because of just how thick the lines are and how much data there is. In the next section, I'll show a different example with a zoom in so you can get a better appreciation for the ability of the cell model to predict the true voltages. But at least here we can see that they're at least somewhat close, and that's a good thing. Well, how did this work? I have some MATLAB code here which illustrates how I produced that exact figure. And what I did, line 1, was I loaded the dynamic test data, and it happened to be in a folder on my computer, which was dynamic file /e2 dynamic /e2 dynamic 35p35. That was the name of the file. And then I also loaded the e2model.mat. So e2model.mat is the MATLAB data file that contains the enhanced self-correcting model parameters of a cell that's called an E2 cell. That's just the name of the model. And so the first file is current versus time and voltage versus time and so forth. And the second file is the data, the ESC model parameters. The file number 1 contained a variable called dyn_data, and it's organized into scripts, just like we saw when we collect the dynamic data. There are scripts 1, 2, 3, I think, and so I use the fields of this variable to denote. Okay, so dyn_data is the overall data object. Script 1 is all the data from script 1, and then time is the time data from script 1 from dyn_data. Voltage is the voltage field. Current is the current field. In the test data, as I go from one step in the script to another step in the script, sometimes the cell tester will repeat a time. It will say, oh, this was done at time 55, and the next thing was also done at time 55, and my model doesn't like that. So I will remove duplicate time steps, and that's what's happening here. So I'm looking for the indices in my vectors by finding places where the difference in the time vector is less than or equal to 0. So if it went backwards or stayed the same. I'm being a little cautious there. I'm really looking for where it stayed the same. So equals 0 would have been the same thing. What I do then, time index plus 1, I delete the second one. I say, I replace that value in the vector with an empty value, so I delete it. Same with the voltage and same with current. So I'm just deleting here the duplicate time steps in order to not confuse my poor simulator. Now the tester, even if I ask it to collect data every second, it tries to do that, but instead of reporting that it collected data at time 0, 1, 2, 3, 4, it will report the actual CPU time on the computer. So it tries to do it every second, but it's not exactly every second. And I'm going to interpolate the data in order to get a synthetic data set where it is actually sampled every second exactly in the data set that I create, because that's the assumption of the model. The model assumes a constant sample rate. So T1 is the first time in my data set, T2 is the last time in the data set. I would like a sample rate of 1 second, and so I create a desired time output vector, which is goes from T1 to T2 in steps of delta T, but I'd also like to start at time 0, so I subtract T1 from the result. And then I get current and voltage by linearly interpolating the original data set at even 1 second increments. So all of that is loading data and conditioning data so that it meets the assumptions of the constant sample rate and that there's no repeat entries, and it's ready to simulate. Here, vest, I'm estimating cell voltage by calling simcell.m. The first input is current versus time. Second input is temperature, which is 25 degrees Celsius, which, by the way, I indicated to myself in my file name as plus 25. This is the sample period, delta t seconds. Model is a structure that is loaded from e2model.mat, and it has all the ESC parameters in it. This is the initial state of charge of the simulation. I've got 2 RC time constants, so those are the initial resistor currents, and then this is the hysteresis initial state. So together these are the initial state, and that's all that I need in order to be able to simulate this cell. And it does, and it creates vest. Once I do that, I open a figure, I clear it, I plot t over 60. T is in seconds, t over 60 is in minutes. It's a little easier to read. So t over 60 with the voltage that was measured from the file, and t over 60 and the estimated voltage from the sim cell. And then I put in a legend, and I put in some X labels and Y labels, and I do a title. And that's how we got that figure there. And this data file will be available on the book website, and you can download these data files. You can download them. You can copy this little piece of MATLAB code and paste it into MATLAB and run it. And assuming that your paths make sense, you might have to modify those. You should get the same figure that is plotted here. So that's an example of how to use it. So simcell.m does all of the tricky work, the hard work of simulating the cell model, and you can open that up and see it and see how it works. But then I just do some preconditioning of the data, then I simulate it, and then I plot it, and that's all there is to it. Sometimes, well, I would say usually, what I've just shown you is sufficient. All I want to do is simulate a cell. And this is something that's safe to do. I'm not messing with the internals of how the simulator works. I don't need to know how the model variable here stores inside of it all of the ESC parameters. But sometimes that might be interesting to me to know what is R0 for this cell, or what is this parameter, or what is that parameter. And it's possible to just poke around at the model data structure and get that information out. But that idea really makes me concerned. My initial degree was in computer engineering, and they taught us all kinds of things about data hiding and proper ways of accessing data, and And you don't want your code, your main code, to directly access fields in your data. You want to use a function that does that for you, because if I ever change how the model data structure works, I really want to change only one function which says how to access it. I don't want to go through hundreds or thousands of lines of code to figure out what else I need to change if I change something in model. So I was taught it's not good programming practice for your main MATLAB code to mess with the internals of the model directly. So instead I provide inside the toolbox a few more MATLAB commands that provides ways of accessing this data more safely. So suppose you want to determine the open circuit voltage relationship at one or more values of SOC. I provide a function called OCV from SOC temp, where temp means that it's temperature dependent, and you can use that. So for example, you could load the e2model.mat file again from whatever directory or folder you stored it in. You say, well, I want to know the voltage at every SOC between 0% and 100% in increments of 1%. Well, the SOC variable is not in percent, it's a fraction, so I say z equals 0:0.01:1. So that goes from 0 to 1 in increments of 0.01. That's the SOC input vector to the function. I say my desired temperature might be 25 degrees Celsius, and then I can plot z. My independent variable is the z variable, and then my dependent variable is the function OCV from SOC temp evaluated at the z vector, the t number, and using this model that was loaded from the file. So that, again, OCV from SOC temp does all of the tricky bits of computing open circuit voltage. If you remember back a couple sections, we said that this calculation was relatively straightforward. It was a table lookup and an interpolation, and that's what that function does, but it does it in a way that is very efficient in MATLAB. MATLAB has an interp1 command which has so much error checking inside of it that it is really, really slow. And it handles some general cases that we don't need to worry about here. So the OCV from SOC temp does its own interpolation function, and it's a lot faster. I once wondered why one of my battery estimating codes was running so slowly, and so I ran a MATLAB profiler, and I found that 90% of the time was inside the interp1 function. And when I rewrote my own interp1 function, the code ran almost 10 times faster. So that's why this is written a little bit differently there. That's one advantage of making your own accessor function to the data, like I've done, is that you can optimize that in one place, and then everywhere that uses it realizes the advantage of that optimization. Well, I can also do the reverse operation. We didn't talk about this, but if I make an OCV versus SOC relationship, I can also invert that to make a SOC versus OCV relationship. It looks something like that. And the code, the process OCV, does that and stores that. So if I want to know what is the state of charge, if I already know the OCV and the temperature, this is how to do it. I can again load the model file. I can set a vector of voltages for which I want to know the SOC point, and I set a temperature, and then I can plot or compute voltage against SOC from that voltage. And finally, if I want any of the dynamic parameters, I have an accessor function called getParam_ESC that you can use in order to get that parameter value at that temperature. So I load the data file, I set the temperature, and I say, oh, I want to know the hysteresis gamma function, so I set that equal to getParam_ESC. gparam is the name to use to get the gamma parameter, and then t and model are also inputs. So how did I know it was gparam for gamma? Well, someone had to tell you, and there's a table on this page that has all of the variables that are stored in the ESC model data file. So there's a name parameter that says what the cell type is. There are fields describing open circuit voltage. So these three together describe the OCV versus SOC. These three describe SOC versus OCV. And then these all describe the dynamic parameters. These are the temperatures at which the data is stored. And then there's a Q parameter, an eta parameter, a gamma parameter, a hysteresis M parameter, a hysteresis M0 parameter, an R0 parameter, an RC parameter. And this is actually a vector of RC parameters if there's more than one. And an R parameter, which is a vector of resistances if there's more than one resistor-capacitor pair in the model. So that gives you an idea, I hope, of how to use the MATLAB codes that are available to you, and I hope you will try them out. And if you're taking this course, you will try them out as part of your homework and get an idea how they work and what kind of results you can achieve from them.